Chapter 4: Stochastic Processes. What exactly is a stochastic process? The idea is surprisingly intuitive. Imagine you're recording a signal, say the voltage across a resistor, or the number of customers walking into a store. If you could rewind time and run the experiment again, you'd get a different trace each time. That collection of all possible traces, all possible time histories, is a stochastic process. For each individual run, called a realization, the process looks like an ordinary signal, but at any fixed instant, across all those realizations, the values form a random variable with its own probability distribution. So a stochastic process lives in two worlds at once, a collection of signals and a family of random variables indexed by time. Now, most real-world processes are too complicated to analyze in full generality, so we look for simplifying properties. The most important one is wide-sense stationarity, WSS for short. A process is WSS if two things don't change when you shift time. First, its average value stays constant, the mean doesn't drift. Second, its autocorrelation function depends only on the time difference between 2 points, not on their absolute positions. That second property is the real workhorse. It means the relationship between what happens now and what happens 1 second later is the same, no matter where you start the clock. And because the variance is just the autocorrelation at zero lag, the variance is constant too. This is weaker than full stationarity. A process can be WSS without being strictly stationary, but it's enough for most engineering applications. Let's look at the autocorrelation function more closely. For a stationary process, the autocorrelation Rx of tau is defined as the expected value of x of t times x of t plus tau. At tau equals 0, Rx of 0 equals the mean square value, the total power of the process. And since the variance, sigma squared, equals Rx of 0 minus the squared mean, the autocovariance at zero lag is exactly the variance. Two more essential properties. First, the autocorrelation function is symmetric. Rx of tau equals Rx of minus tau. Second, its magnitude never exceeds the value at 0. The absolute value of Rx of tau is always less than or equal to Rx of 0. This makes sense. The strongest correlation any signal has is with itself at the same instant. Here's a question that matters in practice. We usually have only one recording, one realization of the process. How can we estimate its statistical properties? That's where ergodicity comes in. An ergodic process lets us replace statistical averages, averages across all possible realizations, with temporal averages, averages along a single time record. On the left, the statistical approach, integrate the probability density. On the right, the temporal approach, integrate one long signal over time. If the process is ergodic, these give the same result. The mean square value, the variance, even the autocorrelation, all can be estimated from a single observation. This is why we can measure the noise floor of a receiver by just recording its output for a while. The chapter covers several important types of stochastic processes. First, the Gaussian process. Every finite collection of samples follows a joint Gaussian distribution. It's completely characterized by its mean and autocorrelation. A special case is Gaussian white noise, which models thermal noise in electronics. Its samples are decorrelated and independent. Second, the Markov process, where the future depends only on the present, not on the full past. A discrete Markov process is called a Markov chain. Think of a telegraph signal encoding Morse code. Third, the Bernoulli process, a discrete time sequence of independent coin flips. And fourth, the Poisson process, discrete events occurring continuously in time, like customers arriving at a post office. The number of arrivals in any interval follows a Poisson distribution. Here's the key takeaway. Stochastic processes are the mathematical language for signals that carry randomness. Two properties make them tractable: wide sense stationarity, which ensures the statistics don't drift over time, and ergodicity, which lets us estimate those statistics from a single recording. Together, they bridge the gap between probability theory and real-world signal processing. Thanks for watching. Stochastic processes are everywhere. Now you know the language to describe them.